In this video, we're going to look at a few miscellaneous rules for calculus, including rules for differentiation and for integration. We're going to start by looking at the product rule for differentiation. Now, an example of where you might want to use the product rule is if you have two functions multiplied together and you want to differentiate what that product is. So here's a physics example. Let's say we've got some harmonic oscillator, some sort of oscillator, which is damped. So the displacement of the oscillator at a time t is given by this cosine omega t, but the amplitude function is an exponential decay. So the amplitude is decaying away with time. Well, in this case, you've got a function multiplied by a function, sure, multiplied by a function as well. But we're going to have to use the product rule to break this apart. Now, why might we want to differentiate this? Well, remember that the first derivative of displacement is velocity. So perhaps we want to know what the velocity is of a particle undergoing this sort of oscillating motion at a time t. We're going to have to differentiate this function. Well, let's start where we started with the first differentiation we did in the beginning of this series. This is how we determined the method for differentiating polynomials. So I started with some function, and I said that the gradient of that function is the first derivative. And so I added a little bit extra on to the x-axis value and found the gradient. And if you want to have a look at that, go back to one of the previous videos. I'll put a link below. So instead of h, we can substitute our f times g, the product of these two functions. And I can do the same thing here. Remember that this bracket notation means that f is a function of x plus this extra bit, and I was using e for the extra bit. It's better than trying to use h for the extra bit, because I've used h for the product of the two functions. I don't want to use delta x notation because I'm using that here, and I'm going to make that difference e approach 0 later. Now this next step's a little bit peculiar, and oops, I've gone off the screen. Let's move that across to here. So this next step's a little bit peculiar. I've included two terms here that cancel out. I've added f of x multiplied by g of x plus e, and then I've subtracted it as well. And you may think, well, why am I doing that? Well, all will be revealed. Because I'm allowed to do that because I haven't actually changed the numerator at all by adding and subtracting the same thing to it. So now what I've done is factored out the function g of x plus e here, as you can see, and I've factored out the f of x here, as you can see. And from this, you can see where all the terms have gone. And importantly, you can see why there's the minus sign here and the minus sign here. Now, looking at those arrows and highlighters probably makes things look more confusing, so let's get rid of those arrows. Next, we can split this fraction into two, and then you start to recognize parts of this. In fact, I'm just going to rewrite this in a slightly different way. Here I've written it slightly differently, but now you can see this term here, we recognize that. That is how we originally derived the expression for working out the derivative of the f of x. So this is just the derivative of f of x. And this term over here is just the derivative of g of x. And if you're not sure about that, look back at that derivation video. So when we use the limits that e approaches 0, this thing here becomes dh by dx. But also this term here, g of x plus e, approaches g of x. So where we had our h function of x, which was just the product of f and g, we can now work out what the first derivative is by doing the product of the first derivative of f multiplied by g plus the product of f multiplied by the first derivative of g. There are some other notations that are sometimes used for derivatives. So if I say a equals bc, then we can say that a dot is going to equal b dot c plus, there we go, plus bc dot. Because that's another notation that's sometimes used for derivatives, and two dots over the top would indicate a second derivative. Another maybe slightly more confusing notation I've seen mathematicians using is a little prime symbol to indicate the first derivative, and two primes would indicate a second derivative. And so maybe these are easier to remember than this mess here, I don't know, but that's called the product rule, and you can use that all over the place. Following on from the product rule, we have integration by parts. probably the most useful of all the integration tricks that we're going to go through. For brevity and simplicity, I'm not going to include the brackets saying what the function is. We're just going to say all these functions are functions of time, so I can use the dot notation. And this is just the product rule that you looked at previously with respect to time. So h is a function which is the function f multiplied by the function g. They're both functions of time. And the first derivative of h is found using this product rule. Now you can see I can simply multiply through by dt and then integrate, and I get this here. Well, this left-hand side part here is the derivative and then the integration. Well, they're reverse processes, so I can just call this h. So this just becomes h equals the integral of the derivative of f multiplied by g with respect to t plus the integral of f multiplied by the derivative of g dt. Now, if I subtract this from both sides, I get this. And in fact, I could rewrite that without the h. We can just put fg in here. So what this means, if I have a product of two functions, and one of the functions is a derivative, then I can more easily calculate what the integration is. So g dot, remember, was dg by dt. Well, g dot dt, the dt's will cancel, leaving just dg. And you can do the same thing with f dot dt. F dot dt is df by dt multiplied by dt. The dt's cancel, leaving just df. I'm sure that's very interesting, but as a physicist, it's this term on the left that's far more useful. So all you do with this, when you have two functions that are multiplied together and you want to integrate them to find the area under a graph that represents the product of those two functions, is you pick which one is f and which one is the derivative of g. You can actually take this one step further by integrating g throughout. And you might find that a little bit easier. So I've just integrated all the g's. The first derivative of g integrated with respect to t gives you g. And then g becomes the integral of g becomes the integral of g. So you might find that easier. Either way, you've got to pick which part of your combined function is f and which part is g, or g dot if there's one that's easily differentiable. So what you want to do when picking which of the functions should be f and which one should be g is you look at what happens. F differentiates. And, well, in this case, g just integrates and then integrates again. But f differentiates. So you want to pick a function of f that gets easier to work with as you differentiate it, not harder. And also g we're going to integrate, and in this example we're going to integrate it twice. So you want to pick a function of g that when you integrate it, it doesn't get any more tricky. So exponentials are a good example here. If we had an expression with an exponential in it, exponentials very easy to differentiate. So we could go ahead and use that as our f, because it doesn't change at all. And g when might be some other function, which we'd integrate twice. And integrating polynomials is quite straightforward. It does actually work either way around, but it just gets more and more complicated. And look, just try it out. You'll get a feel for this. As you work through problems, as you try to integrate them by using integration by parts, if you find that your problem becomes more complicated and further from being solved, you've picked the wrong function to be f and the wrong function to be g. So try again and try them the other way around. We're not going to practice that here because this is about physics, not maths, and you'll get plenty of practice of that with maths. But there's one miscellaneous rule which comes up again and again and again in physics. So it's so important. And it's this one. It's the idea that if you integrate 1 over x dx, you get the natural log of x. Seems very, very peculiar. So we need to dig down and understand why. So let's start by saying that x equals e to the y. Now, if that's the case, dx by dy will also equal e to the y. We can rearrange this, dividing through by e over y and multiplying through by dy, and we get this. And then we can integrate both sides. When we integrate both sides, well, this is just 1 over x, because e to the y we defined as x. And this bit over here is just y. Well, look, if x is e to the y, then y is the natural log of x. That's the notation we use for logs. This is log to the base e that gives you x is y. The logarithm with the base e that gives you an answer of x is y. That's what that means. So that was a little bit more straightforward than all the other miscellaneous rules we've done, but you'll use this one far more in A-level physics. You'll use this one whenever you derive an exponential decay. So capacitors and radioactive decay are two examples, but you'll also use this when you're looking at things like amplitude decaying over time for a lightly damped harmonic oscillator. Or you might use this when you look at how temperature changes over time as temperatures converge towards some room temperature. Just to show you how that works, for radioactive decay, we can say that the rate of change of the number of undecayed nuclei is proportional to the number of undecayed nuclei. And the minus here is because it's a decay, so this is a negative gradient. But what we're saying is that if there are more nuclei, then the rate of decay is higher. And we know that's the case. Now we can write that as an equation like this. We can then rearrange it and integrate it. We integrate it to get rid of these small intervals, dn and dt. This part on the left just becomes the natural log of n. And this part on the right is just minus lambda, which is a constant, multiplied by d. And we can then raise e to the power of this equation. But don't forget there's a constant. The laws of logs means we can split this into this. And when t equals 0, n equals e to the power of c. c is a constant, so e to the power of c is a constant. And that means that e to the power of c is the number you had when time was 0. And there we go. So any sort of decay, exponential decay, you can derive by using that rule. So in the next video, we're going to look how you can construct your own models and use calculus to solve them.